السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم جميعا وكل عام وأنتم بخير بمناسبة بداية شهر رمضان. رمضان مبارك على الجميع. وإن شاء الله اليوم مكملين معاكم في شرح السكشنز لمادة الديناميك. المرة الماضية توقفنا وخلصنا سكشن 19.2 وحكيت لكم حرجع وأشرح سكشن 16.8 لأنه هذا السكشن كنا تاركينه للرجعة للجامعة. ولكن واضح إنه مش رايحين نقدر نرجع للجامعة، حشرح لكم إياه على تكنيك الإيليرنينج. Okay, so section 16.8 talks about relative motion analysis using rotating axis. So احنا as a reminder للإشي اللي عملناه في هذا الشابتر شابتر 16، خليني أرجع فيكم في السكشنز لورا. So هذا الشابتر 16 وكان بيحكي، طبعا احنا كنا لما بدينا بشابتر 16 كنا مخلصين الحكي عن شابتر 12. شابتر 12 كان بيحكي عن البارتيكل. So بدينا نحكي عن شابتر 16 وبدينا نحكي عن الكيناماتكس للريجيد بودي. okay. وبهذا الشابتر بدينا بمجموعة sections 16.1 up to 16.3. okay. وعرفنا فيه أنواع الحركة للريجيد بودي. okay. حكينا عن translation، حكينا عن الروتيشن، وشفنا بالترانزليشن الكيناماتكس سواء displacement للفيلوسيتي ولا الاكسلريشن، ونفس الاشي رحنا شفنا الكيناماتكس للروتيشن about fixed body velocity والاكسلريشن. تمام. وبهذا السكشن تعرفنا على الريليشن بين الفيلوسيتي والأوميجا وبين الاكسلريشن والألفا. هذه الأشياء كلها عملناها في هذا الشابتر، وشفنا الأوبجكتيف طبعا لإله. وبعدها رحنا على section 16.4. بدينا نحكي عن طرق حساب الفيلوسيتي للجنرال بلين موشن. لأنه احنا في section 16.2 و.3 حكينا عن أول نوعين حركة translation rotation. بعدها رحنا انتقلنا للجنرال بلين موشن وأوجدنا الفيلوسيتي باستعمال الابسوليوت موشن اناليسيس. حكينا من البداية بنوجد علاقة بين الثيتا والديسبيسمنت. وبعدها بنوجد الفيلوسيتي. هذا كان في 16.4. طريقة حساب الفيلوسيتي للجنرال بلين موشن كان إلى عدة طرق. هذه أول طريقة الابسوليوت موشن اناليسيس. الطريقة الثانية كانت الريلاتيف موشن اناليسيس لحساب الفيلوسيتي. relative motion analysis طبعا للجنرال بلين موشن again. في عنا الطريقة الثالثة لحساب الجنرال بلين موشن velocity اللي هي instantaneous center of zero velocity IC method. وبهذول 3 sections أنهينا الحكي عن حساب الفيلوسيتي، وبعدين انتقلنا للسكشن اللي بعديه 16.7 وحكينا حنستعمل هذا التكنيك لحساب الاكسلريشن relative motion analysis اللي هي نفس طريقة حساب الفيلوسيتي في سكشن 16.5. okay. وكتبنا معادلاتها. طبعا كنا بنعرف مثلا إذا بنحكي عن اللينك بي سي لأنه هو اللي بيحصل عليه جنرال بلين موشن. إذا كنا بنحكي عن سرعة بي سي relative velocity equation VB plus omega cross product RB with respect or RC with respect to B. okay. سمينا هذا الترم اللي هي relative velocity VC with respect to B. وجينا اشتقينا هذه المعادلة في هذا السكشن. okay. وطلعت معنا معادلة الاكسلريشن اللي هي AC بتساوي AB absolute acceleration سميناها، وحكينا this is equal or plus alpha cross product relative position vector RC with respect to B minus omega squared RC with respect to B. وسمينا هذه طبعا both of them اسمهم A B with respect AC with respect to B. This one called tangential, AC with respect to B tangential. وهذا AC with respect to B. So هذه كانت في section 16.7. وكمان بدي تلاحظوا إنه كان دائما إذا كان في عندي سلايدر كان سلايدر دائما connected with the ground. So from one side connected with one of the link and from other side connected with the ground. أغلب الأسئلة لو ترجع 16.7 هتلاقوها بهذه الطريقة. طيب so section 16.8 هسه بنحكي عن relative motion analysis. نفس العنوان أيوه relative motion analysis للأكسلريشن، ولكن هون حنستعمل الروتيتنج axis. okay. في كل البروبلم السابقة كان الأكسس يحصل له translation only without rotation. هون حيحصل له الأكسس حيحصل له two things translating and rotating at the same time. So the objective is to investigate the relative motion and rotating the frame of a reference. Okay, so هنشوف الموشن لما يكون الريفرنس بيحصل له rotating، لما يكون الفريم of a reference بيحصل له rotating. To demonstrate the problem solving strategy for relative motion analysis using rotating axis. طيب so إذا بنيجي بنطلع very quickly على هذول النوع من الأسئلة وباجي بسألكم سؤال هذول النوعية من الأسئلة مين فيهم بيطبق على 16.7 ومين فيهم بيطبق على 16.8 عشان تعرفوا تجاوبوا. خلينا أفرجيكم هذه. طبعا هذا السؤال زي هيك هذا يطبق على 16.8. ليش مباشرة حكمت؟ لأنه السلايدر زي ما انتم شايفين which is fixed and rotate with link AC زي ما انتم شايفين. So this slider rigidly connected on AC and it freely rotate with the link OD as you can see. So this slider has two motion actually. The first motion is a translation with the link AC. Okay, so here is the track. Okay, and at the same time it slides on link OA. So it has two motion. So if we take a look to this, to these examples, one can simply says that the slider here, for example, in this problem, is only doing sliding, okay, on this link, okay, on this link, only sliding. And in this link, again, only in this mechanism, only sliding. Why? Because this link is fixed to the ground, okay, so it's only sliding. In this scenario, this slider is only sliding again. In this scenario, the slider is only sliding. So if the slider does only one type of motion, then we can go and say that we can solve it by using the previous knowledge from section 16.5 and from section 16.7. Okay. So هذه أسئلة تعتبر من section 16.7 only translating. Okay, so we have acceleration AB as absolute velocity, and here is the relative velocity. We have tangential and we have normal simply. Here the same, we have only this component for relative velocity and those are absolute. Okay, now if we have a problem like this, so I'll ask you which one of these examples applicable for 16.7 and which one of them is applicable to section 16.8. Take like 1 minute. You can pause the video and try to think and determine which one of these examples applicable for section 16.7. Okay. Uh, if your answer was all of them is sections applicable for section 16.8, then your answer is correct. Okay, so all of this example only applicable for section 16.8. But why? You cannot benefit from section 16.7 only. Okay, you must use section 16.8. Why? Because, for example, if I start with this scenario, so here is the slider. Okay, here is the slider, and the slider here is rigidly connected to the disk, so it rotates. The first type of motion is rotation with the disk, and it's freely sliding inside this channel on link AB, which doing rotation. Okay, so it is sliding on link AB. Okay, freely sliding, translating from one point to another, and freely rotate and rigidly connected on the disk, so it's rotate with the disk. Here the same. Okay, so the slider is sliding with link CD and rotating with link AB. So for this one, for example, so here, where is the link that doing general plane motion? Where is it? This link AB. Okay. So here in the middle we have this slider. So this from this point onward, it will extend or contract. So this link AB can rotate at the same time it can extend. Okay. So here the slider will has say two type of motion, rotation, okay, and in the same time translating. So let's see another example. This runner, for example, here this disk is rotate. So this runner will rotate with the this disk, and at the same time he is starting from origin from the centroid, and he is running toward the circumference. So he is translating. At the same time, he is rotating with the this disk. This cooler or ring has two type of motion, translating, sliding on this link, and it's rotating with this link, okay, because this link is rotating also. So it is sliding uh, forward or backward, and it is rotating at the same time. So two type of motion. This connection has two type of motion because it can be slides, okay, as these two links rotate. So it is rotate and slide at the same time. Okay. So this example of relative motion sliding connections has two independent motion, rotating and translating. In the previous examples, the slider will do only one type of motion, which is sliding only, okay, because it's connected on the ground. On this type of example, it's not connected on the ground, it's between two links, this link and this one. In this scenario, it is not connected on the ground, it is sliding on a rotating, so it is slide and rotate on a rotating link. Okay, so two types of motion, two independent motions. So take a look to this rigid body in a blue color. Let us first try to notice the most important things written on this figure. So here we have point, observation point, okay, we can call it, for one sitting on this point and observe this rigid body. So we'll take it as a reference. So this reference, its name is X capital letter, Y capital letter, or X and Y uppercase. Now this rigid body, I can relate point A and point B with respect to this point but you can see that this rigid body translating from this point to there, at the same time it rotates. So this rigid body translate and rotate. So you can notice that this frame, this coordinate system is rotating. Okay, so it is not, you cannot say that point A has this coordinate system. This coordinate system actually rotates with certain angle. So here is the rotation, new location. So the axis is rotating. So is this going to affect the value of the relative velocity, for example, if we start with the velocity, or is it affect the position equation? We'll see. Okay. So is this rotation of the frame will affect the equation that we used to use in the previous sections? So let's start with the position vector. Okay. Using the vector addition, the three position vectors are related by the equation. Where are they? We have RA, we have RB, and we have RB with respect to A. Okay, so RB, the position of point B with respect to A, is equal to, so position of RB with respect to A for a body that doing general motion and translate and rotate. So it's equal to position of point A, where the frame, the original frame, is translate on A, and at the same time it rotates. So in the previous sections, the original frame is translate only on point A, and point A remain unrotated. Okay, only point B, the rotation happens to point B only. So here we have two scenarios of motion: translate of point A and then rotate. So the frame on A, the translating frame on A is rotating only. This is the problem, that this frame is rotating. It's not only translating. Plus RB with respect to A. Here the main notation is that the lowercase xyz and lowercase direction ijk coordinate system assumed to be both translating from this point to this point, okay, and rotating. It rotates with certain angle with respect to fixed uppercase xyz uppercase direction ijk coordinate systems. Okay, here even you can tell that this dimensions related to the xy lowercase coordinate system or xy rotating frame. Okay, and here is the same x lowercase of point B, the location of B in the x direction. So RB with respect to A measure with respect to the moving frame. Okay, so previously we measured this one from the fixed frame. Now we are measuring it with respect to moving frame. You know very well that this relative position vector is equal to the magnitude. If I want to travel from A to B, then we'll travel from here to there first in x direction with this magnitude xp. So we'll move xp in I direction, okay, at this instant. Then we'll move in y direction with this magnitude, okay. So we'll move this magnitude in this direction, and we'll move this magnitude in this direction in y direction, okay. Now, since this rigid body do two types of motion, translating and rotating, so this is at state 1, for example, or at time equal to state number 1, okay, or at time equal to 0. After certain minutes, this rigid body will rotate more, so it will be in, say, in a new position. Okay, so this is x, the x lowercase, and this is y lowercase. So what are the variables here with respect to time? Previously, the frame was fixed, so the only variable was x and y. Now, if the direction is vary, also the direction, those are the direction with respect to time, then now because of rotating the axis, those uh, are becoming variables also. So here we have two variables, and here we have two variables. Why I and j become variables? Because of rotation. Okay, so if I wish to find velocity equation, so d by dt each term, so here we'll have a very complicated derivation. But before, because we are talking about a frame that is rotate with respect to fixed frame, okay, in addition to the rotation of the rigid body itself, then we'll benefit from a new symbols, okay, where omega, this omega represent the or equal to omega angular velocity or theta dot, and omega dot or alpha is the angular acceleration or theta double dot. Okay, so these symbols are special for body that is, or for a rigid body that is rotate and translate. Okay, but we'll assume them equal to the original omega and alpha, as we'll see when we'll start solving problems. Okay, so don't panic, please. If you do not understand anything from the theory explanation, you will 100% understand it when we start solving problems. Okay, so velocity, how we can find out velocity for a slider that is translate and rotate. So the velocity of point B, for example, okay, determined by taking the time derivative of position equation. So the position equation is equal to RB plus B equal to RA plus RB with respect to A. Okay. So if I take the time derivative, this is absolute position will be absolute velocity, nothing's changed, the same. dRA with respect to dt is equal to VA, absolute velocities, nothing changed. The only change will happen in this parameter, d with respect to dt. As you remember, RB is with respect to A is equal to XB, lowercase, multiplied by its direction, plus YB with respect to J. Okay. So here we have two variables, here we have two variables. Now we'll derive them with respect to time. So this relative position, rotate and translate. Okay, translate x and y will change; they will be variable. Rotate axis I and j will also become variables. Okay. So if I insert the derivation to this relative position vector, xbi plus ybj, so the derivative will go to the first variable, then it will go to the another one, plus, so here we have two variables, so مشتقة الأول, first derivative multiplied by the second, plus first parameter multiplied by the derivative of the second one. Okay, plus same thing will happen the other parameter. Okay, so here the derivative for the first one, then the derivative of the second one. So here derivative of the first multiplied by second plus the first multiplied by the derivative of the second. So here I'll do certain arrangement. I'll put this term and this term together. Okay. and this term and this term together. Okay, only arrangement. So here is this term and this term together, and the other two terms together. Okay, so here you can tell easily. We'll come to it. I leave it. Okay, but here, in order to get rid of this derivative of the direction, we must benefit from this diagram. Okay, here is the rigid body. That is, this is the secondary xy coordinate system, or the rotating xy coordinate system, lowercase. After certain minutes, it will rotate. Okay, after certain seconds, it will rotate. Okay, with amount d theta. Okay, so this distance represents di. The arc here is equal to di. So the transferring from this format to the final format through these steps is not required. Okay, so this step is not required, but it's good to understand what happens while we transform from the position relative equation to velocity relative position equation. Okay, we reach up to this format. Okay, we write VB equal VA plus this term. Okay, plus this term. Still we derive this term. Okay, we reach up to this one. So this term, we gather these two terms together and these two terms together. So these two terms represent the velocity of point B with respect to x, y, z coordinate system. So this is relative velocity of B with respect to x, y, z system. And this term represents the rotation of d theta of the x, y, z axis. Okay, so this term can be written as VB with respect to A for x, y, z coordinate system, and this term, it can be written as omega cross product xb in I direction plus yb in j direction. Okay. Okay. So how we transfer from here to there? From the knowledge of this picture. Okay. As I told you before, this is the arc. Okay, di, and this is the theta. Okay. So I can substitute in here, or I can take it outside, and you know that omega and xb, both of them are, so I can transform it to the cross product. Okay, same thing happens here. Okay, this is the arc, this is d theta, this is dj. Okay, so you can write it instead of dj with respect to dt, omega cross product yb in j direction. Okay. Okay. So yeah, this is the end of derivation of the relative position vector. Okay, this is the final result. Or I can write it instead of xbi plus ybj. Instead of it, I can write the relative position vector rb with respect to a. So omega cross product rb with respect to a. So we'll take this result and substitute it in the relative position, in the relative velocity equation. So VB equal VA plus this term, which is complicated as we mentioned. So instead of this term, I can write this equation in here. So VB equal VA plus VB with respect to A, XYZ plus omega cross product RB with respect to A. So if you compare this equation with the previous section, the equation in the previous sections, you can tell easily that this term we already saw it before, but the only new term is this one. because of the rotation of the secondary coordinate system with respect to the original fixed coordinate system. Okay, so what we can understand from this equation, the first term is the absolute velocity of v. The two terms here is the absolute velocity of v on the xyz frame. Okay, this is very similar to the original equation without the last term. Okay, this last term is the relative velocity of v with respect to a. So it is a relation between the secondary coordinate system and the original coordinate system. Okay, and here is the explanation for each term. Now this is the velocity equation for a rigid body that does two types of motion, translating and rotating. Okay. Acceleration, what we'll do, we'll take the time derivative for this equation. So the time derivative for the first term can be written in this format. The second one, dv over dt. The third term, we have two variables. Okay, so the first derivative of the first cross product the second plus first cross product the derivative of the second plus the time derivative of the relative velocity. Okay, here the first three terms, this one and this one and this one, is straightforward because instead of this one I can write AB directly. Acceleration, absolute acceleration of point A, of point B. Here, absolute acceleration of point A. This one, the omega with respect to dt is omega dot or alpha. Okay, so it is direct. This one, omega cross product drb with respect to dt, will go through same steps as in the previous slide. So I can write the direct answer for this one, which is, remember, we named this terms as dr d with respect to dt for whom? For rb with respect to a. So I can write the final result. So instead of this term, I'll remove it and write this one. Okay, so here we have omega cross product, this bracket. Okay, plus d of relative velocity by dt. This is another complicated derivative. We'll write the final result. Okay, so as you can see, the first term very simple, acceleration directly. The second term the same, very simple. The third term is omega dot or alpha cross product rb with respect to a. This one, as I said, omega cross product, instead of drb with respect to a over dt, I'll write this one in here. Okay, so it will be omega cross product the first term. Here it is, omega cross product the first term, this one. Okay, plus, because here we have plus, omega cross product the second term. Okay, because the derivative we saw earlier. Now the derivative of the last term is equal to omega cross product VB with respect to A for the XYZ frame plus the relative acceleration of the secondary frame. Okay, so in order to move from here to there, we have very long story. No need to show you the steps of the derivation. Okay. Or you can tell easily that here we have this term and here we have same term here, so we can add them together. So instead of writing both of them separately, we can add them. So here we can notice that we have 2. Okay, so 2 because we have 2 terms. This term will go down like this. This term as is. This term as is. So nothing will change. and this term as is. Now, how we can compare this equation with the previous equation in the previous section 16.7? Here it is. So you can tell that this equation up to here represent the 16.7. Why? Because this is represent alpha, cross product RB with respect to A. Here the cross product give us, I showed to you earlier this one, which is equal minus omega squared RB with respect to A. And I explained before why it has become minus. So instead of omega squared, I can write this symbol. The only new two terms is this one and this one in the acceleration equation when we have body that do both type of motion. Okay, so this is absolute acceleration of the origin. This is the tangential acceleration alpha cross product r, and this is the normal acceleration omega squared r, okay, with minus sign of course. And this term, its name is carrierless acceleration. And this type of acceleration appears when we have two type of motion. Okay, so if one problem come and ask you find carrierless acceleration, so no need to go through all of these equations. Okay, it will be very big mistake. So if I ask you to find carrierless, only come and say carrierless is equal to this term plus the relative acceleration of the object. So as we mentioned, that this up to here, up to this limit, this is absolute acceleration of point P on the XYZ frame. And these two terms represent of translating the secondary frame to the original frame. Okay, what is carrierless acceleration? If we have here 2 point of view, this is top view. I look at this from top, and I look at the black pole from when I'm standing on this red color. Okay, so the inertial frame of reference, upper part of the picture, the black object moves in a straight line. So if I come and take a look from top, taking a top view as an example, and does this start rotate at this direction, and this ball start to translate, I'll see that this black ball will move straight downward, okay, only translating. However, if I'm standing on the red point here, for example, and this disc start to rotate, I might see this black object will rotate. That means the carrierless acceleration responsible for the two type of motion, translating and rotating. So carrierless acceleration, whenever a point is moving on a path and the path is rotating, there is an extra component of acceleration due to the coupling between the motion of the point on the path and the rotation of the path. This component is called carrierless acceleration. Okay, so it is the coupling between rotation and translating. It's correlated or discovered by the French engineer Carrierless, and it's named after him. Important, this type of acceleration or this component of acceleration is very important in studying the effect of force and acceleration of Earth rotation on the rockets and long-range projectiles. Okay, because here we are facing the two types of motion. The rocket translate, and at the same time the Earth is rotate. Okay, so we have a coupling. We need to consider the relative coupling between them. because Earth doing translation and there is gravity acceleration affecting on the rocket, so it will rotate with the Earth, and at the same time it will translate far away from the Earth. Okay, so we have coupling. This coupling we call it Coriolis, and it can be calculated by using this term. Okay, we can calculate the Coriolis effect to omega cross product VB with respect to A. Now I will delay solving this problem until the next lecture. Okay, so again I will explain for you very important steps in order to be able to solve these type of problems. Here, if you take to this picture, you can tell easily that this problem only solved on section 16.8. Why? Because the slider is not on the ground. It is hinged between two links. One of them fixed connected, so it is rigidly connected with link AB, and it's free to translate on the other link. So this is always happen. One of the link will be rigidly connected to slider, and the other link will allow to the slider to slide on it. Okay, and of course, if we are asking you to use section 16.8, will provide you with the equation. Okay, so if you go back to the data sheet, you can notice that those equations are given in the data sheet equation. And by the way, you can delete, for example, the last two terms if we have normal acceleration, normal relative acceleration, as we saw earlier in section 16.7. The same for the relative velocity. You can delete the last term if you don't have Coriolis effect. Okay, only like the previous sections. Okay, and also I'll solve this problem, and you can tell easily that this problem is solved, can be solved on section 16.8. Why? Because the slider is rotate with this length and slide on this length, so it has two independent motion. If we have for the slider two independent motion, that means we must benefit from section 16.8. So next time I'll start with this simple example. It will be a very long one, but it is a simple scenario, and we'll end up with this example, and this example will be the most difficult scenario. Okay, so until then, stay safe and